In this lecture, we will learn about Kirchhoff's current and voltage law. They are shortly abbreviated as KCL and KVL. These two are basic laws of electricity and dictate how the voltage and currents in a circuit will behave. Once we see these laws, I think you will agree that this is very intuitive and basically nothing new, yet very powerful. We actually encountered KCL in lecture 7 where we showed that current is a scalar quantity. Summary of that discussion would be, since charge can neither be destroyed nor created, total currents entering a point or a node would be equal to the total current exiting that node. As we can see here, the total current entering this node is 4 plus 3, 7 amperes, and the total 7 ampere current is exiting the node through the only outlet. In general, if we had I1 and I2 current coming in and I3 current going out, we would have I3 equals I1 plus I2. That's all what KCL says. Now that we know about circuit symbols, let's use lines to represent wires instead of physical wires. And you can imagine maybe there are elements at the end of wires or something like that. So this is a node, and when we talk about KCL, we are talking about currents entering or exiting a node. So KCL is completely related to nodes. Let's try an example. Given the values of I1 and I3, can you calculate the value of I2 using KCL? Yes, just put the values in and the value of I2 will pop out. After knowing all the values, this is what it looks like. And as you can see, it all makes sense. The total current going in is 1.5 plus 3.5, that is 5 amperes, and that's the total exiting current as well. So KCL holds. KCL also works in case of negative numbers. So let's say I3 is negative 5 amperes and we want to figure out I2. As usual, we put in the values and pops out the value of I2. Now let's see if putting in these values actually makes sense. We know that if we flip the direction of the current and negate its value, the current remains same. So negative 5 amperes of current exiting the node actually means 5 amperes of current entering the node. And similar case for 6.5 amperes of current. And now as you can see, all of this actually does make sense. So total current entering is 1.5 plus 5 amperes, which is equals to 6.5 amperes, and the same amount of current is going out of the node. So the gist of this example is you don't have to worry about negative currents. KCL will give you the correct answer nonetheless. Going back to our general case, we had I3 equals I1 plus I2. We can rewrite the same thing on one side of the equation. So this equation just says the total current exiting the node minus total current entering the node must be 0, which is obvious because they are equal, right? Now, because KCL doesn't care about whether the current is negative or positive, instead of subtracting, we can just write addition of negative of the entering currents. And visually, it will represent that all the currents are going out, positive or negative. So now all of these currents are just exiting the nodes, and this gives us a tighter form to write the KCL. Summation of all currents is 0. It's as if all the currents are exiting the node, and so the sum of all currents will be 0. Of course, this is not possible without some of them being negative. Even though this gives us a tighter form to express KCL, I would advise you to just subtract entering currents from total outgoing currents. And let's make this a convention. If we see a current exiting the node, we will add them, and if we see a current entering the node, we will subtract them. Let's try an example. In this example, 1 ampere and negative 3.5 amperes of currents are exiting the node, so we add them. And since 2 amperes, negative 3 amperes, and negative 1.5 amperes are entering the node, we subtract them. And according to KCL, the sum must be 0. Formally speaking, KCL just says the algebraic sum of all currents in a node must be 0. The word algebraic is important. We don't just want to normally add up everything. We want to add up some of them and subtract some of them. That's what means to do algebraic sum. Now, in the last lecture, I gave you guys two golden rules. I showed you equations you get from components. But I didn't actually show you the equations you get from nodes. KCL are those equations because KCLs are applicable in a node. So oftentimes KCL is also called node equation. By the way, here's a summary of all the component equations you have seen in the last lecture. Notice that I have followed passive sign convention in all of these cases. Current is flowing from positive terminal to negative terminal for all of these components. Now let's see how we will apply KCL in an actual circuit. Here's a circuit very similar to the last lecture circuit. We still have the same three nodes. Since the bottom node is grounded, its voltage is 0 volt. And the node on the top left corner would have 1.5 volts because that's what that 1.5 volt voltage source is doing. That voltage source is creating a 1.5 volt voltage difference between the two nodes. And since the lower one is 0 volts, the higher one must be 1.5 volts. That's why that node is 1.5 volts. Similar logic applies to the top right node. That 2 volt voltage source makes sure that the node has a voltage of 2 volts. If you actually built that circuit and measured the voltages, that's exactly what you would get. Now, as your second golden rule suggests, every component should have one current. Because we don't know what their value is yet, I'm calling them I1, I2, I3, and so on. If you could actually build this circuit in real life and I asked you, what's the current? You could just measure them and give me the answer. But can you tell me from just this circuit diagram? We actually can deduce what all the voltages and currents will be without even actually building the circuit in real life. Because we have a lot of equations. Namely, we have 3 node equations from 3 nodes and 6 component equations from the 6 components. Our job is to solve those equations and figure out the values of currents and voltages. This is what we call circuit solving or circuit analyzing. It's very important to theoretically calculate the voltage and current values because if we try to build a circuit in real life without knowing how much current or voltage to expect, we will be putting human lives in danger. And in general, if you want to build a circuit, you need to know if it works before you actually build it. So my question here is, how can we figure out the currents of this circuit? We have already figured out the voltages. So let's focus on this one node and try to write KCL equation for it. Let's call this node 1. Because I1 and I4 are entering the node and I2 and I3 are exiting the node, we will have this equation. So this is our node equation for node 1. Next, for node 2, we have this equation. And for node 0, we will have this equation. Now, how do we figure out the currents from these node equations? Let's focus on just one equation. Remember, node equations aren't the only equations in our hand. For example, this current source will directly give us the value of current from its component equation. That's a more complicated way to say than it actually is. You can just see that the current will be 0.5 amperes from just the figure. So we have figured out that the current I3 will be 0.5 amperes. Can we find out any more current? Yes, we can. From this 10 ohm resistance, we can use its component equation to figure out the current. Because we know the voltages on both ends and its resistance, we can use resistor's component equation, aka Ohm's law. We get the current to be 0.05 amperes. We have figured out the value of I4. Let's put it in the node equation. Similarly, we can figure out the current from 2 ohm resistance. We have I2 equals 0.75 amperes. Now for I1. Up until now, we have used component equations to figure out what the current would be. Let's see if we can use component equation for that 1.5 volt voltage source to figure out the current I1. And if you tried that, you will immediately see that you will fail. The reason is there's no current in the voltage source's component equation. So no way you will get current from that. Also, we have already used this equation when we figured out the node voltage. If we assumed the node voltage to be X volts, we would get the X from this voltage source equation. So it helped us figure out the voltage value, but isn't helping us with the current. Is there any other way we can figure out the value of I1? Of course, this is where the node equation comes in. We already know all the currents and I1 is the only remaining unknown current. So we can use it to figure out that I1 is actually 1.2 amperes. So you can see how KCL can help us figure out unknown quantities. You can go ahead and figure out I5 and I6, but I won't do that. In the next video, I will show a systematic way to do all of this which applies to any circuit. For now, it's good enough to show that KCL and KVL are very capable. Next, we have KVL. This will also seem obvious to you once I explain it. But first, what is it actually? Let's start with the example this time. What KVL tells us is that if we take any loop and if you add up all the voltage differences, you will get 0. So let's focus on one loop and demonstrate what it actually says. So if you imagine walking along the loop, you will encounter a lot of components. And if you add up the voltage differences of those components, you'll get a total of 0 volts. Keep in mind that you have to follow passive sign convention here as well. So when you are walking over a component, make sure to take the plus minus sign in such way that when you are walking, you are always walking from positive to negative terminals. And if you do that correctly, all the voltages should add up to 0. Now, there are a few ways you can explain why this happens, but I actually just like to write what we are adding up. And you can easily see that if you add them up, everything just cancels. So, of course, their sum would be 0. In fact, you don't even need to know what the voltages of the nodes are. Let's say the voltages are V0, V1, and V2. Even without knowing the actual node voltages, you can guarantee that the sum of the voltage differences will always be 0. And that's all KVL says. So just like KCL is useful for solving circuits, so is KVL. KCL is applicable for nodes, KVL is applicable for loops. KCL says what happens to the currents in a node, and KVL says what happens to the voltage differences in a loop. So I hope you can see how similar both KCL and KVL are. And just like KCL is useful in solving circuits, so is KVL. I won't go into the detail here because the main focus of this lecture was the actual statements of these laws. On that regard, this is what KVL says. The algebraic sum of all the voltage differences in a loop must be 0. And that's it for this lecture. See you in the next one.